Okay, so this one I made a little easier than I intended to, but easier, I should emphasize, not easy. Easier is probably better on our first go through with this. So what I asked you to do was to do a net electric field. We gave the positions. I should be clear that this position is L for my test probe charge down and L over 2 to the right, so it should be directly in line with my positive probe charge. And I want to be consistent that I labeled this one as 1 and this one is 2, and I want to say that Q1 equals Q2, but Q1 is negative. So other way of thinking it is Q2 equals negative Q1, whichever you want to say. All right, we want to do the sum of our fields. The first thing we want to start with is doing in our vectors. So I look at my test probe charge, and I need more space. My test probe charge next to a positive charge, well, it is going to be repelled straight down. It's going to be repelled straight down because it's what is happening here? Give me a vector. All right, it's going to be straight down from the positive charge is being repelled away from. What's happening with this negative charge? Well, one of the things I want to do here, and actually let me erase what just happened with the positive charge. We'll come back to that in a second, because I think part of what I have been seeing some of you get hung up on is this right here. How do you take the dimensions that you've been provided and convert that then into components for your electric field? One of the things we know is that our electric fields, we're looking at a straight line, right? So if I'm looking at a straight line between the point I'm at to the point that's causing it, then I know that those dimensions there are going to give me something like this. There. And by the geometry of how things are placed, I can make myself a little triangle right there. Let's take a different color and a different line. So because we are going point to point, we're not like taking a ride away from the two charges, we're just this straight line. Whatever geometry I have laid out that I know about the position of my charges and the position of my point, I can use those to get the trigonometry for my field components, because they won't be the same size. We don't know what they are, but they will have the same proportions. I'm going to have a similar triangle within that much bigger triangle that will be my actual electric field. So if I can figure out the angle just based on a position triangle, that angle is going to apply to my electric field. So then I can apply that to figure out my components for my x and my y. So in this particular case, what would I have? My positive test probe charge is going to be what? Attracted to the negative. So this is exaggerated. I'm just kind of following the outline. That would be the direction of my resultant vector. If that's the direction of my resultant vector, then let's see what's happening here. My y vector is pointing straight up. This would be like my e in the y vector. So that's kind of handy. I know that it's going to be positive. It's pointing in the positive direction. And my x component, what color do I want? I don't want that. My x component, let's go with red. My x component is just going to be following right along the x-axis, pointing in the negative x direction. So that would be my E1 in the x, and this would be my E1 in the y. And this would be my E1 resultant, or E1 net, however you want to look at that. So once again, the size, the length of each of those lines, I don't know yet. But I know the proportions are going to be the same as the triangle I have for the position that I've used to create this triangle. So I'm going to capitalize on that. And so what do I know? For this triangle, for this side here, I know that I came down in L. And for this side here, let's see, L over 2 plus L over 2. That's 1/2 plus 1/2, so this is also L. So if I want to create my x and y components, well, I can choose either side because I'm going to know that this side here is going to be what? The square root of L squared plus L squared, otherwise known as the square root of 2L squared, or L times the square root of 2. So I have all three sides. Choose which one you want in order to create your angles, or to choose an angle that you want to solve for. For me, I look at it and I'm like, okay, you know what? I'm going to live life on the danger side. I'm going to go ahead and choose this angle here. Why? Just to remind you that sine and cosine aren't always lined up directly with x and y. You just kind of get in the habit of that. So let's see. For the y, what do I have? Let's see, I have this angle here. My y is touching, so I'm going to have something like cosine of theta. And what does that equal? Well, I know the proportions. Sine of theta, or cosine of theta, well, this length is L, equals L over hypotenuse. Well, over hypotenuse is the square root of 2L squared. And as I just said, we can simplify that. And I can pull the L out. Square root of L squared is just L. So I'll get L over L root 2. Simplify even more and rationalize the denominator. And I get something like this, root 2 over 2. And some of you are yelling at the screen right now saying you've just made this way too involved for what it should be. This is obviously a 45-degree triangle, and what you obviously have to know, especially if you had me last quarter, is that nothing is ever going to be just a 45-degree triangle. So follow along with the steps on how to do it, and you'll be golden. Now let's take a look at our x component. Our x component then is sine. The x side is on the opposite side of this angle that I chose. So I have sine of theta equals opposite, well, this entire length L over hypotenuse to, oops, backwards, L root 2. So that also is root 2 over 2. And if my inside joke about yelling at me for overcomplicating things didn't immediately become apparent to you, because they have the same sides, so many of you probably recognize this is a 45-degree triangle, but still want to be able to do the steps. So make sure you're comfortable with that. Okay. Now I have the ability to break everything into to its x and y components, which is what I need. And I know, let's see, my y is going to be positive and my x is going in the negative direction. It's going this away, so it's going to be negative. So now I can write my E1 then. It's going to have what? It's going to be E1. Let's start with our x. We said that's negative, so it's going to be negative E1 times the trig function. So times sine theta. And then, let's see, let's do my y component. I've defined that as going up. It is positive, so plus E1, and this is x hat, sorry, plus E1 cosine theta y hat. And then me being me, and because this is going to save you, otherwise you'll have a lot of difficulty in the next section when we do our complex fields. I'm going to tell you, you are never allowed to use sine or cosine. You must define things in terms of proportionality. And for some of you, this won't feel comfortable because a lot of us get in the habit of writing these things down without recognizing that they mean the exact same thing. If I say cosine theta equals root 2 over 2, I know it's proportionality. I don't actually need to solve for cosine of theta to figure out what theta is, to turn around and put cosine of theta into my calculator to multiply it by the electric field because they equal each other. So this, what I have here multiplied by whatever my E is for the E1 is going to give me the proportion of the field that's in the x direction. So I'm going to have then negative E1 times square root of 2 over 2 in the x hat plus E1 times root 2 over 2 in the y hat. And I will insist that you do things in terms of the fractions rather than the angles. You're not putting any angles in there. Cool. Now, let's do this. Let's go ahead and define what E1 is. Well, we figured out what the distance is. So remember, E is the kq over r squared, the charge creating it, over the distance squared, so the distance away it is. Well, in the process of figuring out our x and y components, we figured out what the hypotenuse is, so we know what r is. So r equals L squared, let me erase, equals L root 2. So r squared is going to equal L squared times 2. See if that makes sense. If I square the square root, I'll get 2, and my L squared stays L squared. So now I can rewrite this then, that I have then my E1 is going to give me negative k q over r squared 2L squared times the square root of 2 over 2 x hat plus kq over, let's move this down a little bit, plus kq over 2L squared root 2 over 2 in the y hat. Sweet. So we just did the hardest part. The one we don't have yet is this attraction, then the one I erased. So we have this vector here. For the positive to the positive, I am, whoops, that's horrible. Let's do that again. Here's my probe charge. I'm looking at this positive charge and saying what's going to happen to it. Well, my positive test probe charge is going to be repelled away from. So it's going to have a vector component going in the negative y. So my E2, and only in the y, my E2 then is going to be negative kq. Both my q's have the same charge magnitude, just different in sign, over r squared. Well, the distance away is L squared. L squared. That's it. Let's see. This is in the y, so I just need to make sure I make this clear. This is in y hat. That's it. Run through that again. I know that this vector here, I'm looking specific to this charge now, is pointing away from that positive charge. E fields emulate away from the positive charge. Passing me up, it's going in the negative direction. There's my negative sign. The distance away is L, so over r squared is L squared. The sign, the magnitude of the charge is just Q, and I know that I have my y hat. So now, using superposition of fields, I can say that I'm going to add, just straight up add my x and y components of each. So my E net, let's do a different color. My E net is going to equal then, I'm going to have only one thing with an x hat, so kq over 2L squared root 2 over 2, I should have simplified that, x hat. That's what's happening with my y hat. Then I'm going to have this plus kq over 2L squared root 2 over 2 y hat minus kq over L squared y hat. Oh boy. Okay, to simplify this, I need to multiply this by 4. And does that even make life any prettier? I don't think it does. So let's see, KQ. My dog's hungry. That's why she makes those noises. Root 2. She is not dying, honestly. Over 4L squared. Let's see, plus, I'm going to make my life easier and factor out my KQ. Just make it a little easier to see what will simplify and what won't. What am I left with? Oops, X hat. I am left with my root 2 minus 4. And all of that is divided by my 4L squared y hat. And that is my E net. I know, I have a landline. That blows everyone away. That's it. So that's as pretty as I can make it. I would have to have a Q value to make this more simplified. One of the things I could do if I wanted, I could factor out the K, Q, and the 4L squared. So I'd have root 2 minus 4 in my y hat, and I'd have negative root 2 in my x hat. So what that tells me is that I'm going to end up with a negative y hat. So that tells me that my repulsion is going to be stronger than my attraction. So when I look at my positive charge to my negative charge, it's a bigger distance, so that's not entirely surprising. That should be kind of intuitive there, that the one is going to repel more than the other. So I'm going to end up with a resultant vector that looks something like this. They're both going to be going in the negative direction, so I'll have like a y vector coming down and an x vector coming like this. So I know that my final resultant vector is going to be something like that. And there you have it. So practice with these skills. On the handout, I gave you a couple challenge problems, or questions more or less, just to look through and move your test probe charge all around. Play with the vectors, get comfortable with this. Next week what we're going to do is more involved charge configuration. So now we're going to do like charges spread out over an entire rod, over an entire circle, or an entire sheet, and we'll talk about charge densities, and then we're going to start integrating. And that is the big reason why I want you to be able to do this, to define your angles in terms of those proportions rather than in terms of theta, because what you're going to find is in doing that step, we're going to make things easier for ourselves moving forward once we start throwing calculus back in there. All right, that's enough for now. Control. Ships.